complicated because there's no p-values, there's no variability, there's no statistics involved. I went through 31 slides, 38 slides. Not one p-value. That's not necessarily bad. The computer scientists have never looked at a p-value in their life. Most computer scientists have never seen a p-value. That's not true because they take an undergraduate statistics class. But in their actual work, they don't do it from a statistical approach. How are statisticians and computer scientists different? We both deal with data, right? We both have, there's theoretical statisticians, there's theoretical computer scientists. Those theoretical people are more like mathematicians than anything else. The statistician has p-values and variability, and the computer scientist doesn't. The statistician's concerned with models. The computer scientist is only concerned with results. In my question right here, do we need a model? Or should we just throw it into a neural network and classify it as best we can? If our only goal is classification, a neural network or some other artificial intelligence approach might work better. But we have 111 data points. A computer scientist will look at 111 data points and say, well, come back when you have 11,000 data points. And their approach will work well. A statistician with 111 data points said, well, I need a model. I only have 111 data points. What do you do if you have 2,000 data points? Like, not sure. Sort of borderline between the computer scientists and the statisticians. So this is where you need to know that if you have a huge amount of data, then artificial intelligence makes sense. If you have a small amount of data, you're stuck with the statistical approach. And where's the border? It depends on the situation. Can't tell you that. Other than 10,000 is a lot and 10 is a little. You're stuck in between. Okay. Let me show you some, where do we want to go? We're going to go to our element data. So it turns out that this data is a good example of different, remember, back in the beginning of cluster analysis, I talked about the different distance measures. Turns out different distance measures yield dramatically different results for this data. So if I'm playing with cluster analysis with this data, then I might, first of all, color my data points by origin, which is what we've done before, and just run a cluster analysis. So cluster analysis, remember, uses all the dimensions of the data, and it clusters the points together. So you kind of expect the green ones might cluster together, or they might not. Analyze, multivariate, cluster analysis, and this is what the agriculture people might do before they come to see me. You go, oh, somebody told me that cluster analysis is helpful, and what do I want to cluster in this case? These are all the elemental variables. And I stick them over there, and now I'm going to, based on all the measurements for all the elements, I'm going to see how they group together. And because I'm a default kind of person, there's some choices over here that we're going to talk about. But the top choice is one called Ward, which is It is the most common. The statisticians like Ward because it's a sum of squared things, and it makes sense from a statistical perspective. The computer scientists like other choices. And the default down here is to standardize the data. So it's before it's clustering them, it's making them all have mean 0 and variance 1. Is that good? Don't know. But it's probably not a bad idea to choose the default to start with. By the way, I could have written a bunch of SAS code to do this, right? I choose not to do that. And what I can see, because I colored it by where they're actually from, and the coloring is not part of the clustering is not using that information. Clustering is only using the elemental information. And so there's the blue guys. They're clearly close to each other. And finally they get joined with, there's one weird green one right there, which turns out to be the interesting data point. If I scroll down here, the red one, this thing is called a distance graph, and it's a measure of how far apart we'll talk about that a little bit. It's a sort of like the cubic clustering criteria. The red guys are all down here. The blue guys are all here. And so we've got those, and I'm sure this is the two, Malawi and Brazil, right? I can go and look. But maybe I should make sure that the red and the blue ones are the ones I got right. There's the red and the blue ones. Blue is Malawi and red is Brazil. So the cluster analysis is supporting the fact that Malawi and Brazil are different from each other and are grouped together. And the principal components and other techniques do the same thing. And there's a good outcome up here as well. Remember, your goal is to understand the data and to realize that Kentucky and the U.S. are similar to each other is obviously geographically logical. And so here's the orange, I don't know which one is the U.S. It doesn't matter which one is the U.S. and which one is Kentucky, but it's all mixed up in here, right? So we have evidence that Kentucky is part of the United States. Sometimes we don't think so, but it is, and that result is completely logical. So should I put this picture in my paper? Maybe. It supports my conclusion that something is going on with the data. If you click on this little diamond guy, it puts a line in here and tells you how many clusters you have. So how many clusters do I actually have? The correct answer is probably something like this. That green guy is weird, right? But except for the green one, so this one, when it's right here, which was the default that the software chose, it's looking like 5. Which makes, so this is the red ones are all together, the blue ones are all together, these red and greens are the U.S. and Kentucky all mixed up, and we got weird point number 6, which actually groups to the blue one, which was Brazil maybe, instead of grouping over here. So one of the points is weird, number 6. So just for fun, and I can't remember, principal components. We'll do the same thing. Take all these guys, put them over here, and do principal components. And blue guys, red guys, all mixed up. Do the plots say the same thing? Yeah. Which one's better? They're different from each other. If you do the cluster analysis, someone's going to ask for the principal components. You do the principal components, you're going to get a reviewer that says, oh, you should try clustering and see if it tells you anything. Should you put both in the paper? Completely up to you. But now I want to find out, oh, I bet this is 0.6 down here. Yep. I always forget about that point when I make the PCA plot. There's a stupid green one down here. Probably probably there's some mistake in the data, would be my guess. Because, and this is why the cluster analysis is having trouble deciding, excuse me, if it's over here or over there. Because it's not anywhere. So really, there are 4 clusters according to the principal components in my data. There's the US ones over here, the 2 countries here, and then there's the one weird point. And the cluster analysis found that as well. So that's good. Okay. Back to my cluster analysis. So there are choices to be made in how to do the cluster analysis. The default method is Ward's method, and I was going to